Ladies and gentlemen, now introducing me. Hello, Internet. Let's fade down my little drum beat there. Hey, happy Thursday. What's up, Internet? I'm your host, Joey, here on Everyone Loves Math. It's awesome to see you on this Thursday. It's really awesome to see you. Love it. Let's see. Updates for me. So, I did miss the stream last night. I'm here tonight. I'll be here Monday. All next week. We got it. I did get a haircut this morning. That's an update. We've met the microphone. All right, so I battled with this microphone. I tried to use it today. This is just way too much up in my face. So what I'm going to do is I'm going to make it so that the microphone is like lower, like this. You know what I mean? But I have to move it around. And then I'll have a little bit more microphone confidence and microphone self-esteem. New to this Twitter thing. Wait, this isn't Twitter. See, that's how new I am. New to this Twitch thing. And I know a good Twitch streamer needs one of these. I know you need one of these crazy microphones. And it looked smaller on Amazon when I bought it. Okay? Just know, I mean, on Amazon it looked like this big. The box was so small. So that's one update. Update number 2. I am recording my own music for Twitch and my upcoming YouTube videos. And you'll hear some new music next week. Just something to do to keep my creative juices flowing. Let's do our other update. We might as well do our little ad for the day. Today's show brought to you by everyonelovesmath.com. Everyone Loves Math is my website. So if you go on there, that's me, man. Everyonelovesmath.com. I've said it before. I'm going to say it again. Take that, all you .org people. You got to get with the .com business. So there's no new update on the website, but just a reminder that there is a link to tutoring. So if you like what we do here, want to go a little bit deeper, and want to go one-on-one, you can book a session now. I've got all of my availability for the next 60 days up online, and you can click that link to book a session. We also have the Everyone Loves Math message boards. Really, there's 2 levels. We got a free level and the Everyone Loves Math supporter level. The only difference is one of them is $5 a month. And so for those of you that have $5 a month to donate to the cause, I'd love to have it. The other thing that you get with Everyone Loves Math as a supporter is it gets you kind of the VIP question and answer section, which you really don't need right now, but if this website gets popular, then you might need it. Okay? Let's see. So that's message boards, and then and then remember, if you miss me in between these shoots, there's also a picture of me on here. You can right click on that baby, right? Right click Save As, and I'll be with you always. Okay. So I think those are the updates for today. What we've got on the docket. Let's talk. So first of all, good evening, Twitch chat. What I do for each of my shows, which is Monday through Thursday at 9 p.m. Eastern Time, I go on to Reddit. I steal questions from the Homework Help subreddit, and I do them up here. But I'm only doing the questions on the Homework Help subreddit until I get questions in the chat. And so if you have a math question, you can put it in the chat. Or you can take a picture of it and send it by text to the Everyone Loves Math hotline, which is coming, 727-371-6464. So there's all kinds of ways there. See, there's the phone number. That's a Google Voice. You're not going to interrupt me. It's all good. So there's all kinds of ways to ask for help. I'm here to help, and just to find an excuse to do a little math. You know why? Because everyone loves math. I don't know if you've seen all the stuff. Okay. All right. So that having been said, let's go to our first problem. I'm excited to do it. So when I went on the Reddit, I saw a couple questions that hadn't popped up before in the last couple of weeks, and I thought this was a really neat one. So for folks watching, the thing that I think is really neat about this problem is this problem is a calculus problem. It could be a calculus problem. I certainly did a problem like this in calculus, but you can also totally get this problem right in Algebra 1. So that's cool. All right, so let's, all of that having been said, let's get to it. I'm ready. Let's see here. I see my little doc. Boom. All right. So in this problem, it wants us to find an area of a region bounded by some lines. And if you've never done a problem like this before, you have no idea what I'm talking about. But let's start by looking at this region. So we've got 3 lines. One of those lines is y equals 3x. One of them is x equals 2, and one of them is y equals 0. So let's see, I'll just do them in order. 3x, so this is a line where the y-intercept is 0, and the slope is up 3 over 1, right? This is y equals 3x plus 0. So we end up with something that looks kind of like this. That's our 3x graph. Okay? Y equals 3x. All right, if we want x equals 2, then let's see, I'll use a different color. Use a different color just to be beautiful. We can use x equals 2, and x equals 2 happens to be this vertical line right here. And then for my third trick, let's see, we'll do black ink. The third line is y equals 0, which is another word for the x-axis. All right, so they gave us these 3 lines. I just graphed those 3 lines, and now they're talking about the area of the region bound by those lines. And now we know what we're talking about. Look at this. Look at this. It's a little triangle. It's this little triangle. There it is. So the crazy thing about this is you could give this problem to a calculus student and they could take this thing and do way too much. Or you could give it to like a middle school student and they know that the area of a triangle is 1/2 base times height. And so we have a triangle. This is a right triangle that's standing straight up. So we know its base and we know its height. We can just look at it. So let's take a look. I'm going to use red to mark out the base. So if we look at the base is down here. That's 2 units. The base, it's a skinny triangle. It's 2 units wide. And then for the height, let's see, I would probably just want to count. 1, so I'll use my red. So here's 0. 1, 2, 3, 4, 5, 6. So the height of this triangle is 6 units. And so even though this problem is written in a really, like, you know, it's a way that would impress grandma, I would definitely say, right? Find the area of the region bounded. 1/2 times 2 times 6. 1/2 base times height. And if you work this out, this comes out to be 6, and we would say something like 6 square units. All right, because they don't give us inches or anything like that. All right, that's one question done. Woo! Woo, you love it. You love one question done. Happy Thursday, everybody. Happy Thursday. So I saw that question. I was like, ooh, that'd be a good, like, first question. You know, do our patented math squats. And then I saw this one, and I was like, oh, man, what a great follow-up question. We should get these people together so that they can do math together. Maybe that, you know, whoever asked those questions, maybe there's a love match that we just haven't seen yet. All right, so this one's a little bit funkier because now we've got like 3 variables, but let's do it. It says, find, in terms of k, the coordinates of the points where the line 3x plus 4y equals k cuts the x-axis and the y-axis. Okay. Find the terms of k. If the area of the triangle formed by 3x plus 4y equals k, and the positive x and y axes is 24 square units, positive x and y axes, find the value of k. I'm going to make a, you know, I put this problem on here. This just has like word salad. I'm actually going to skip this problem. I'm sorry, Twitch. That problem had like some word salad. I changed my mind. It's Thursday. I can do whatever I want. I'm just going to move on. Sometimes, you know, sometimes when a teacher asks a question, they get too crazy about themselves. I think that's what that question. That's what I'm going to blame it on. That wasn't me. That wasn't me. Let's talk about this one. Here's a gnarly word problem, right? Look at all these words, and of course it's about ancient Greece. So there's all these super fun names. We're going to work past it, and we're going to answer this question together. It's going to be great. Okay. So what do we got? We got Eratosthenes. Eratosthenes. It doesn't matter, right? I mean, this person is extremely dead. So we could call him Steve if we wanted to, even though that's a little offensive. I mean, we probably should get it right, but Steve is very dead. So Eratosthenes was a Greek scholar who lived and worked in Cyrene and Alexandria. One day while visiting Cyrene, he noticed that the sun rays shone directly down a well. Okay. On this date, 1 year later in Alexandria, which was 500 miles due north of Cyrene, he measured the angle of the sun to be about 7.2 degrees. See the figure. Use this information to approximate the radius and circumference of the Earth. So I picked this problem for a couple reasons. Number one is it's just a nice little geometry problem for us to think about, and the other reason is that with this thing, we have to use our imagination, see what's going on in this problem, take care of business. So let's see. If I'm looking at this right here, so it was Cyrene right here, where this must be the well where the sun ray went all the way down the well, right? So that must have meant it's basically like this would be a radius right here of the circle. So if we're going all the way down the well, the sun would go straight down the well into the center of the Earth. So we know this dot is the center of the circle, and if that dot is the center of the circle, then we know that that is a radius. Okay, so the other thing that we know is that when they measured again, this degree of the sun, gosh, that doesn't even, I'm sorry, I'm going to go back. That doesn't even look like it. How do we make it look like an R? Oh boy. Oh boy. See, nobody stopped me, and now the sickness is taken over. Should I do capital R? I'm going to do capital R, and now it doesn't just look like some weird curve. Okay, so so if we take a look at this, the sun is shining straight down. Right here, these things I'm pointing to, those are parallel lines. And if those are parallel lines, then this 7.2 degrees is a corresponding angle with that one, which means that this little interior angle is 7.2 degrees. There it was. I wrote 7.2. You see it? It's really tiny, 7.2. So what we really figured out by looking at this was that 7.2 degree angle gave us 500 miles around the outside of the circle. So that's the other thing. I mean, this problem just has a ton of stuff. But that 500 miles, that is not, I'm going to erase it, that is not a straight line like that, because, you know, the Earth isn't flat. That's 500 miles around the circumference. See where we're going here? Okay. So now, how the heck do we move from here? Well, here's what we're going to do, and this is what I love about this so much. This is a proportions problem. We can set this up as a proportions problem. Every day it's a proportions problem. How do I know? Well, because 7.2 degrees, that was 500 miles. Well, if we want to know the circumference of the Earth, then that would be the whole 360 degrees for x miles. We can set up this equation to figure out the circumference of the Earth. And so with this problem, what would we do? We can multiply both sides by 360 and multiply both sides by x. I'm going to tell you right now, this is another reason why I picked it. You're not going to see your boy, that's me, you're not going to see your boy cross multiply. I'm going to tell you that right now. I don't believe in it. Don't believe in cross multiplying. So if you're a cool kid, you do this the quicker way anyway. All right, so we got the 360x for multiplying that on both sides. What are we going to do? We're going to simplify this thing. So the 360 cancels with the 360, the x cancels with the x, and we're left with, what are we left with here? 7.2x equals whatever 500 times 360 is. So let's go ahead and do that using my fancy calculator. That's 180,000. And then to get x by itself, we just divide by 7.2 on both sides. And so this is going to be ugly. Divide by 7.2. Oh, that's weird. It actually came out pretty nice. Came out 25,000. I didn't know that was going to work that nice. So what that means is that this ancient Greek estimated the circumference. Remember, this represented the circumference of the what do you call it, Earth. So that would be measured in miles. Because remember, originally they had measured in miles. So that's our circumference. Good times. Good times. USA. I don't know. I'm feeling. I don't know how I'm feeling today. I'm feeling a little like. I feel like doing math. That's what I'm feeling. All right. So let's move it on. Remember, for anybody that just joined, you can post a question in the chat. You can text a question to the Google number. The ELM hotline. That's just a fancy way to say my Google Voice. And if you do it, I get your text right there, and I've got it on my phone ready to do problem if anybody has a question. Just text me. Okay. So hey, look, it's a new question. I thought this was an interesting one because I haven't said either of those words yet. Get the equation of the perpendicular bisectors. So this is a perpendicular bisecting problem. You love perpendicular bisector. You don't know it yet, but you love it. So let's look at it. I'm going to do the first one. So they give us 2 points. 3 comma 2, and 1 comma negative 6. And what we're going to do, because if somebody is looking at this problem and they're not sure what to do, I'm going to show you how Desmos is your best friend. All right, you ready for some Desmos? Again, Desmos is the best. Desmos.com, everyone's favorite graphing calculator. Boom, it's right there. All right, so in order to graph this thing, I'm going to go to Desmos, and I'm going to put in the 2 points. Negative 3 comma 2. There's one of them. And I can even label that point. I told you all about Desmos before. Desmos is the bomb. If you don't know it's the bomb, it's the bomb. I've been talking about Desmos being the bomb for a good long time. So there are 2 points right there, and I can zoom in a little bit. Okay. So what do we want to do with these 2 points? We want to do a perpendicular bisector. Oh my goodness. So what does that even mean? So with a perpendicular bisector between these 2 points, first of all, we have to find the point that bisects these 2 points. So it's somewhere right around, oh, you can't see that. So it's somewhere right in between those 2 points. So we can find that with the midpoint formula, and then we'll come back and do the perpendicular part. Does that make sense? I can't hear you, so I assume you said yes, that makes sense. Okay, so let's do, let's see, let's take you back here. Boom. Let's do the midpoint. So the midpoint will tell us what's in between, directly in between these 2 points. And I will tell you, as a teacher, I have tutored about the midpoint, or taught the midpoint, I guess. You can call it tutoring. But I have taught midpoint several times. And the thing that blows my mind is everybody wants to make this formula crazier than it is. Halfway between any 2 points is just the average of the x's and the average of the y's. That's all you have to do. Average the x's, average the y's. So let's do it. Let's do a midpoint. I'm just going to say midpoint. And then I'm going to draw it like that as a big old point. And what are we going to do? We're going to average the x's. So negative 3 plus 1 divided by 2. Right? Add them, divide by 2. And then we're going to average the y's. 2 plus negative 6 divided by 2. That'll give us the midpoint between these 2 points. All right, so a little bit of mental math, right? Negative 3 plus 2, or I'm sorry, negative 3 plus 1 is negative 2, divided by 2 is negative 1. So what that means is that the x value that's right in between these two is negative 1. What do we got with the y value? 2 minus 6, right? 2 plus negative 6, that's negative 4. And negative 4 divided by 2 is negative 2. So if we average the x's and we average the y's, we get this point, negative 1 comma negative 2. Now, let's do the good mathematical thing. Let's go back to Desmos and see what the heck we just found with this point. So these were our original 2 points. I'm going to go right here and I'm going to put in that third point, negative 1 comma negative 2. And ooh, can I even label this the midpoint? Can I get that cool? Oh my gosh, I can get so cool. Look at that. So I can even label that point the midpoint. Does it look to be right in between the 2 original points that we were given? Yeah, it looks right in between those 2. Good for us. So when we talk about a perpendicular bisector, I've got good news. We got the bisector part down, right? Because it's got to go through this point. So we bisected the line segment that connects those 2 points. Now we need to go perpendicular. So if we remember back to Algebra 1, perpendicular is all about slopes. So what that means is we need to find the slope of the original line, and then we'll play with it. Okay? So let's do this. I'm going to take a little bit of a walk with this problem because I think it's worth it. I think this problem, if you're in algebra, geometry, algebra 2, this is fantastic. Fantastic practice. Okay, so we found the midpoint. Now let's do the slope. And let's see. Boom. All right, so I'm taking over question number 1. I'm just going to erase these other ones. All right, there we go. Don't grade my work. I'm a little sloppy. Okay, so now we need to do the slope. So this is the slope of the original line. So remember, I used MP for midpoint. I'm using M for slope because everybody does that. Okay, so the slope is you subtract the y's. So we'll do 2 minus negative 6. and then subtract the x's. -3 minus 1. Don't make it any more complicated than that. All right, -2 minus -6 is 8. -3 minus 1 is -4. So our slope comes out to -2. Okay, but you got to ask yourself, the slope of what? And that's where we go back to Desmos to see what's up, okay? So what is up with -2? Well, here's what I'm going to show you. Yeah, let me show you. So the original line going through those 2 points had a slope of -2. So I can't just type in -2. That doesn't do anything. But if I put in another line where the slope is -2, maybe I'll put in -2x, right? So that's a line that is, let's see, ooh, I can even move it down to, can I? No, I can move it down 3 or 4. There we go. Take a look at that. So what I've just done is I've used that slope that we just found and just kind of played with the y-intercept. And now we have an equation of a line that's going through those 2 original points. It's also going through the midpoint, but nothing special is happening there at that midpoint. Okay, so what do we got to do? Well, if we want to go perpendicular, then this is where you got to remember perpendicular lines have slopes that are opposite reciprocals. So the slope of this line up here is -2. So if we take the opposite of that, we get +2. Take the reciprocal of that, we get 1/2. Because reciprocal means flip it upside down. So we get +1/2. Ooh, now look at it, right? So now I'm trying to use my imagination. Let's see here. Maybe I want to, you know what I'm going to do? Just so that we don't have to try our imagination that hard, let me leave in the original line, and then we'll put in a new line with a +1/2 x, and then we just need to move that one down. We can actually solve this problem in Desmos by playing with it. So I did -1. That doesn't look low enough. Let me try -2. Uh-oh, that looks too low. Is it going to be like -1.5? Ooh, look at that. Look at that right there. So the line, this purple line that we made, this line is perpendicular to the original line, and it bisects the line segment. It's halfway between these 2 points. So this purple line that we found really is the perpendicular bisector. The only problem is we found it kind of with cheating, right? Like I kind of used Desmos. So we'll go back and do it like, you know, the real way. But know that like Desmos is there for you to do some brainstorming. Twitch chat, y'all using Desmos? Y'all got to use Desmos. It's so cool. It's so cool, man. So let's go back to our whiteboard here, and let's actually just do this for real so that we can figure out how to get the answer. All right. So I'm just going to give myself some space here. That's right. Desmos is so useful. All right. So if I do my space, we got to talk about what do we know. We know right now that we need a line going through the point -1, 2, right? It has to go through that point, and the slope of the line has to be +1/2. All right, that's not cheating. So let's go back up here. So remember, the point right here, the midpoint is -1, -2. So the line we make has to go through that, and our line has to be the opposite reciprocal of -2, which is, the slope of our line, opposite reciprocal of -2, which is +1/2. And so we're at a spot right now where if I can make the equation of a line that passes through that point and has that slope, then we're done. And it turns out, say it with me now, there's such a thing called point slope. There's the point slope form of a line. It looks like that. And so whenever I'm given a point and a slope, I'm going to use point slope. That's what I'm going to do. So we're going to stick, what are we going to do? I'm going to make some notes. Got to make some notes. 1/2 goes in for m. We know that. -1 is going to go in for x1, and -2 is going to go in for y1. Because for that point, the x is -1 and the y is -2. All right. Y'all, we're ready to write our answer. How about that? So y minus y1. So I could write y minus -2. If I want to write that, I could. Most humans would write y plus 2, but you know. And then let's see, we got the 1/2, that's the m, and then x minus -1. All right, so we could stop right there, but honestly, I'm looking at this and it does kind of make me want to throw up in my mouth like a little bit. So we got to clean up these minus and negatives. How about we make it y plus 2 equals 1/2 x plus 1. When we see minus and negative, we're going to make that plus. All right. So what I notice all the time is like students can do this and then spit out this answer and not really take a step back and see what they did. So that's what we're going to do, and y'all are going to be shocked. Y'all ready to be shocked? We're going to Desmos. Let's go to Desmos to check this. So here's what you might be thinking. You might be thinking, hey, we already kind of know the answer to this problem, and it's this equation, this 1/2 x minus 1.5, and the equation that we came up with doesn't look like that. But listen, there are more than one equation to represent every line. So let's see what happens if we type in this equation. Y plus 2 equals, you see me typing it in Desmos, 1/2 parentheses x plus 1. Now take a look at what just happened. So what just happened was, even though these two equations here at the bottom, even though these are in different forms, the equation y plus 2 equals 1/2 times x plus 1 gave us that perpendicular bisector. It goes through that midpoint just like we wanted, and this line right here is perpendicular to this line. Listen, man, y'all can't ask for anything more than that. All right, that's a beautiful thing. Desmos all day. Desmos all day. I don't know what to say, man. Desmos all day. I love it so much. Okay, so we did it. We did it. And notice, like, especially for, you know, people working at home, like, if you're working at home and you're doing, like, a math, I would have Desmos out the entire time. All right. So, yes, you can read this. This is a little funky. I like this one because we haven't done a ball bouncing yet. So why not? So let's go through this. Oh, and the text is a little weird. Okay, so it says a ball is dropped from a height of 55 centimeters and bounces back up to 70% of its original height. Now, what they need to say in this problem is that it bounces, it reaches 70% of its original height, and then it bounces again to reach 70% of that, and then bounces again to reach 70% of that. And each time it bounces, it gets 70% as high as it did before. Okay, so what's it asking? How high does it get after 4 bounces? Okay, so I think what this problem is trying to do is it's trying to get us to like get a feel for what kind of problem this is. So we can totally get a feel for what problem this is by just playing with it, right? So it's first bounce, right? Let's talk about bounce 1. So what does it happen at bounce 1? So at bounce 1, the height would be not 55 centimeters, but it would be 70% of that. So it would be 55 centimeters times 0.7. So that's after 1 bounce. Okay, after 1 bounce, we are 70% as high as where we dropped it. All right, I'm going to have my calculator out because we got some decimals to deal with. But don't worry, the actual thing that we're going to do in a second is going to be easier than decimals. All right, so this comes out to 38.5. And what a mathematician here might do is they might call this H1, because that's like the first bounce. That's what I might do, call it the first bounce. All right, so now how about we do the second bounce, H2. So what happens with H2? So it bounced, it got let off at 55 centimeters, it bounced, came back up to 38.5, not as high, right? 70% as high. Then it's going to bounce and come up a little bit lower than that, 70% of that. So we can calculate that. You notice I'm leaving some space because something's about to happen, because we're going to do 38.5 times 0.7. It's 70% as high as it was there. So I bust out my calculator, that's why I'm looking down. Multiply 38.5 by 0.7, and we get 26.95. Okay. I'll leave you in suspense. For those of you that don't know, why did I leave a blank? Suspense. Okay. But it's math, so it's like the least suspenseful thing ever. But still, pretend that you are riveted by that suspense. All right, so let's talk about the third bounce. So what are we going to do for the third bounce? So we went from 55 centimeters to 38.5 to 26.95. So for our third bounce, we're going to be at 26.95, but we need 70% of that because it's only going to bounce 70% as high. All right, I'm back to my calculator, times 0.7. How about 18.865? I'll round to 18.87. Okay. All right. And now they asked us about the fourth bounce. So right? Didn't they say that? Am I crazy? It said, how high does it bounce after 4 bounces? So let's talk about the height after 4 bounces. Height after 4 bounces. Well, it's going to be 70% of that 18.87. Because every single time it bounces 70% as high. So here we go. Let's go and calculate. Times 0.7. How about 13.21? So that'd be 13.21, and this would be centimeters. So every time it's bouncing, comes back up a little bit less, 70% less, and after the fourth bounce, 13.21 centimeters. So I would put that in here. How high is it after 4 bounces? 13.21 centimeters. Okay. After how many bounces does the ball reach a height of approximately 19 centimeters? That's a weird question, B. 19 centimeters. Well, thank goodness for us that we already did this work, because let's see, after the third bounce, the height comes out to 18.87 centimeters. It's pretty close to 19 centimeters, isn't it? So I would say, after how many bounces? 3 bounces. After 3 bounces, it comes back to a height of about 19 centimeters. Okie dokie. What is the total distance traveled by the ball when it hits the ground for the 5th time? Okay, well, we did 4 times. All right, we might as well go and work this all the way out to the 5th time. So let's go H5. So H5 would be 13.21 times 70%. And so that would be, I love using calculators, and so do you all the time. 9.24. So that'd be 9.24 centimeters. All right. So here's what they're trying to do, though. This is where we gotta read this really careful. What is the total distance traveled by the ball when it hits the ground for the 5th time? All right. So let's work this out. And what they want to know is for example, after from it being dropped, it goes 55 centimeters before it even hits the ground once, bounces once. So this seems to me to be like a good picture excuse. So let's draw a little picture. I'm going to draw a picture. All right. So, and I just want to go back again here. And it wants to know when it hits the ground for the 5th time. So we want to draw enough of this picture so that we know hitting the ground for the 5th time. All right, so what happens here? So the ball's dropped. Oh, here's the ground. Let's make the ground. Beautiful. That's the ground. So what happens first? The ball is dropped 55 centimeters. And we'll just say everything here is in centimeters. All right, then what happens? Then the ball bounces back up and then comes back down. All right, and maybe I'll make this a little bit taller, because remember, it bounces back up about 70%, well, exactly 70% as high. And so, let's see, let's do something a little closer to 70%, just to make it look pretty. All right, and we know what this distance is, because we've already done the work. Up here, that distance is, after the first bounce, 38.5 centimeters. So I'm going to write 38.5. And I'm not going to label the other one because we know it's the same, right? It's 38.5 the same. So we're talking about 55 centimeters, 38.5 coming up, 38.5 coming down. So now I'm going to also keep track. We hit the ground once there. We hit the ground twice there. All right, so now let's do our picture for the 3rd time. So what happens then? So the 3rd time we go up, not quite as high, and back down. And what was that number? That was the 26.95. That was the next one. So I'm just using what we did here. It's a good thing we did all this work. This is 26.95. And this represents right here hitting the ground 3 times. Okay. All right, so now we're going to talk about bounce 4. So now let's see. It goes up again. We go up again. 70% is high, and then back down. Let's see. And bounce 4, isn't that the 18.87, right? Or is that the 2? Yeah, 18.87. So let's put that in there. And that represents the 4th bounce. All right, and then almost there, we got our 5th bounce coming. All right, so our 5th bounce, we come up 70% as high and then come down and hit the ground for the 5th time, right? Boom. And what's this going to be? Well, we calculated this already. It is that 13.21. So this is 13. Oh, can't use blue, pink, red there. We got to use blue. You know it. So this is 13. Did I say 0.21? I get so into my marker colors. 13.21. Okay. So now we have to talk about the total distance moved by this ball that's been bouncing. So I'm not going to put all this in the calculator, but I am going to write it out so that we know what to put in the calculator. So what do? We're just going to add all these distances up because we've modeled what happens. Bounce 1, 2, 3, 4, hit the ground the 5th time. So what are we going to do? We're going to do 55 centimeters. We're going to add 38.5. You can tell when I start putting decimals. I need more coffee. 38.5. You drink coffee at 9 o'clock at night, and then where do you go? And I'm going to multiply by 2 because remember, it came up. Remember, I'm going to do 38.5 for that, and then 38.5 for that. And then we do the rest, right? 26.5 or 26.95, we're going to multiply that by 2. Plus 18.87, we're going to multiply that by 2. And 13.21, we need 2 of those as well. So if you put that in your calculator, add all that up, then you're going to end up with the total distance traveled with all them bounces. Okay? All right, and I don't know what that is. It's something. It's something. All right, and then the last one here, last little question. There's always math teacher, you got to let them ask a cute question every once in a while. So then it says, what is the total distance? I'm reading, is this part D? What is the total distance traveled by the ball once it stops bouncing? So here's where we do the difference between real life and math, okay? So in real life, we know that if we drop this ball, eventually it'll stop bouncing. However, in the mathematical model of this problem, like in the world of math, this ball always comes up 70% as high as it was before. So even though it's decreasing, it's always going to rebound a little bit. It's going to rebound 70% as high. So what does that mean? We're going to say the ball never stops bouncing. This is a mathematical model. So unless they tell us something about how the ball stops bouncing, the way they've modeled it, this ball never stops bouncing. Now, by the way, okay, so we've answered this question. Yay, good for us. Good for us. I did want to show one more thing because we got to play with stuff, right? It's a Thursday night. It's a Thursday night on Twitch. We got to play with stuff. So let's go back here. Remember this? Hey, remember when we were doing the bounces? Okay, stick with me here because you're going to see how a function comes to be. You're going to see y'all are going to see the live birth of a function right here. No one else is going to offer you that. Okay, so what do I mean by that? Well, look at the calculation that we did here, right? For the first height, we did 55 times 0.7. Okay, simple enough. Then we did 38.5 times 0.7. Okay, well, where did this 38.5 come from? It came from this, didn't it? The 55 times 0.7, 70% of 55. So really, in H2, we could have said 55 times 0.7. That's where the 38.5 came from. And then we multiply by 0.7 again. I'll show you what I mean. This right here, 55 times 70%, that is the 38.5, which is right here, which we multiplied by 0.7 again. So, and you can, if you are well within your legal rights as humans to not trust me, go to your calculator and do 55 times 0.7 times 0.7. I bet you I know what you're going to get. All right. So what's going to happen next? So let's see. In the next line where we have H3, what did we do to find H3? Remember, it was over here. We did 26.95, so we did the previous answer times 70% again. Okay, well, I'm going to copy the previous answer, which was 55 times 70% times 70%, and then we're going to multiply it again by 70%. And again, you can trust me, but if you don't trust me, go to your calculator and do 55 times 70% times 70% times 70%. I bet I know what you're going to get. You're going to get 18.87. All right, so now let's cut to the chase. We're going to do the last two like cool kids, because I ain't writing out all these 0.7s. Think about this. In this problem, I have 0.7 times itself 3 times. Couldn't I have just written 0.7 cubed? You know what I'm saying? 0.7 to the third power. Right here, I got 0.7 2 times. I could have written 0.7 squared. And this is 0.7 to the first power. So if we step back and see this pattern, and then just be kind of mathematically stubborn, which you're going to hear me say all the time, mathematically stubborn, then the next one must be 55. Oh, ooh, 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 ooh. Come on, whiteboard, you got a little wild there. It's got to be 55 times 0.7. Let's see, this was to the first power, then to the second, to the third. This has got to be 0.7 to the fourth. And again, double check. Go to your calculator, check it. And the fifth one, this has got to be 55 times 0.7. Ooh, my typo day. My typo day is Thursday to the fifth power. All right, so what am I doing? Well, it looks like the 55 is always there, the times 0.7 is always there, and then the exponent keeps increasing. And since the exponent keeps increasing, we can give it a variable. Ooh, look at all, ooh, we're hitting them here. So what I could say is I could say instead, I could be like h of x equals 55 times 0.7 to the x. That right there is a function, the function. I'll put a box around it. And they didn't ask for this, but we're going above and beyond because you're doing math at 9:30 at night. So this is the function. Remember, I was talking about that. This is the function that models this ball dropping stuff. And just because I want us to do it, let's go to Desmos and look at this function. I think that's fun. It's my idea of fun. I'm going to take you on this journey. So let's delete all of this stuff. Oh, I remember that problem. Okay. And what we're going to do is, let's graph that thing. It was h of x, so I can put that into Desmos, that's fine, equals, and then it was 55 times 0.7 to the x. Okay, and oh boy, we got to zoom out, don't we? And look at that. Now, I promised you a birth. God, I really regret saying this now. I promised you the birth of a function, and we straight up have the birth of a function. Take a look at that. This is an exponential function. This is exponential decay. And this models, and it's weird because you think about, this doesn't look like a ball being dropped, but remember, this models the height of the ball being dropped. So take a look at this. What if I ask Desmos, what's h of 1? Guess what Desmos tells me? 38.5. And we can go and see it. Where is it? It's right up here. H of 1, all right, there is 138.5. There it is. You see it right there. So sure enough, that gave us the same information that all of that scratch on the other on the whiteboard got us. And I can even ask what's h of 2? 26.95. So this is giving us the same numbers. So this actually does, it doesn't model what the ball looks like, but it models how high it bounces each time. And then remember how I said the ball never stops bouncing? Look at this right here. It kind of looks like it's on the ground right there, but look what happens when you zoom in, man. All right. Don't make a liar out of me, Desmos. I'm zooming in. And look at this. Look at this. You thought that red line was right on the axis. Ho, ho! Ho, ho, ho! Look at that. How do you feel now? So even though it looks like, and yo, look at that y value, right? That y, 0.000392. So with this mathematical model, after, what is this, 33 down here? So after 33 bounces, the ball's going to be like 0.0003 centimeters off the ground. So technically it's still bouncing, but I mean, come on. All right, that's the difference between like the mathematical model and the real life model. So mathematically, it bounces forever. Real life, some other stuff is going on, but yo, you need to get like way further in physics to know what that is. All right, and how do I know? Because I don't know how to answer that. All right, it's just like, yo, let the physics people do the hard problem. The math people, we're going to do the easy one. No, not to say that was easy, but compared to the next one, Okay, here we go. Moving on. I'm going to do a quick commercial break. I just want to remind folks on the chat for something. We will, we're going to take care of business together. Ooh, and I just saw a question from the chat, so we're going to look at that. All right, so reminders. Let's talk about reminders for a minute. So before we do this next problem, I'm just going to remind you here about my website. So, hey, look, here's my website. So just quick reminders. Everyonelovesmath.com. This is where you can go get information about me. There's message boards to ask questions. There's a link for private tutoring, which you can follow there, book a session. I got all of my sessions like 60 days in advance right up there. Okay? All right. So commercial break over. Looking at the clock, what do we got? 9:48. So we got a question from the chat from the ELM hotline. So we're gonna do a problem from the ELM hotline. That's how we're gonna go. All right. So what I'm doing right now is I had a question texted to me, and I'm gonna write it up here. So let's see. Actually, if you give me just a quick commercial break, you're gonna get the question back up here. So give me just a minute, and we'll do this question from chat. And then we'll probably call it a night. We're coming right back. Give me just a moment. Quick commercial break. Hello, Internet. Welcome on back. I think we're going to make this the last problem of the night. However, I'm having a little bit of a problem. getting it on the whiteboard, so we're just going to do it from here. I'm trying to zoom in a little bit more on this thing. All right, so I'm just going to read this to everybody, and it's going to be great. You all ready? It says, you are putting a basketball goal in your backyard. The post for the goal is mounted into the ground with a concrete mixture compared of 30 pounds of crushed rock, 12.5 kilograms of sand, and 4,500 grams of cement. What is the total mass of the concrete mixture in grams? And there are 453.6 grams in a pound. My goodness. Really? This is the last problem? All right. Hey, you asked about it. We're going to do it, but my goodness. Okay. So what do we got? What they really want is we want to know the mass. I'm going to write this down. The mass of the concrete. Okay. So let's go and do that. I'm going to go and pull this up on my little whiteboard. Okay. Boop, boop. Okay. So we're going to do the mass of the concrete. All right. And then, let's see. So the mass of the concrete that we're figuring out it's like 3 different things put together. So the concrete is 30 pounds of crushed rock. Then we have 12.5 kilograms of something else, sand, right? That's in concrete. And then 4,500 grams of cement. Okay, and all of these are being combined to make the concrete. All right, so what we need to do is we need to add these 3 together, because the amount of crushed rock, the amount of sand, the amount of cement, all go together to make the total mass of the concrete. Okay? So of course, now we see what the issue with this problem is. We're given pounds, kilograms, and grams. They want the answer in grams. So I'm just because I want to feel accomplished, I'm going to put a check mark by that one. Hey, look, grams, done. Okay. We need to take kilograms and pounds and convert them to grams. So, hey, I'm going to do the kilograms first. And the reason why I'm going to do the kilograms first is a kilogram is just 1,000 grams. So 12.5 kilograms of sand, that's really 12,500 grams of sand. Because I took 12.5 and multiplied by 1,000, so I got 12.5 thousand. All right, so far, gotta put a little check. All right, now I feel accomplished. All right, so we got our cement taken care of, we have our sand taken care of, and now we need to figure out the crushed rock. So let's go back, let's go to the crushed rock, and this is where we use, I've talked about it a couple sessions ago, we use my funny forms of 1. So we got 30 pounds, and we want to convert that into some number. Ooh, I should probably like scroll so you guys can see this, huh? 30 pounds, and we want to convert that to some number of grams. Okay, now you can't see this because the problem isn't up anymore, but they did tell us how to convert from grams to pounds, and so I'm going to convert using that as a funny form of 1. I'm going to put pounds on the numerator and grams in the, pounds in the denominator and grams in the numerator, so that in this step I can cancel out the pounds and the only unit is grams, which is what I want. So what do I know? Well, the problem says there's 453.6 grams in 1 pound. And so this tells us to multiply 30 times 453.6, which you love to do it. I got my calculator right here. I'm going to do it. 30 beep boop times 453.6. And this comes out to 13,608 grams. All right. And so now if we scroll back up, 13,608, so I can put that here, 13,608 grams. Oh, my little pen goes wild. 1360 0.08 grams. And so now what can we do? Now we can just add these three things together. So we're going to take the amount of crushed rock plus the amount of sand in grams plus the amount of cement. You add those three together and you're going to get the total number of the total number of grams for this concrete mixture, and you'll be able to get the problem from there. All right, ladies and gentlemen, boys and girls, it's 10 o'clock. At this stage of the game, Everyone Loves Math, we are done for the night. So just as a reminder to folks, this show runs Monday through Thursday, 9 to 10. You can send in text, video, take a picture, send in any question to the Everyone Loves Math hotline, and I will be more than happy to address it on the stream. So again, you go to the Everyone Loves Math hotline. It's the phone number that's about to show up, 727-371-6464. Or you can go to the Everyone Loves Math website and ask it in the message boards. Or you can always ask it during the Twitch chat during the live show. Ladies and gentlemen, that's it for me. We'll see you back here if you so choose Monday night. The archives go up on YouTube the next day. Y'all stay classy and have an awesome weekend and evening. Bye-bye.